Hello, hello. Today we talk about statistical testing in linear regression. What is statistical testing and how does it fit in with everything that we've already covered? We are still considering the same scenario. There is a causal effect that we really want to learn about, but that is unknown to us. We have learned that if we have access to a random sample, we can define the OLS estimator. Under some assumptions, this estimator is a good estimator in the sense, for example, that it is unbiased, it is consistent. That's all fine. Now let's suppose that we implement our estimation strategy. We draw a random sample, so all of these here become concrete numbers that we can plug into Stata. Then we'll obtain an estimate. That would be a number, let's say 5. Now, upon seeing this number 5, what are we supposed to believe about the true causal effect? Are we supposed to believe that it is exactly 5? Well, we know that there is sampling error. We know that the OLS estimator has a variance and makes random mistakes. So we probably shouldn't think that it's exactly equal to 5. Should we at least believe that the true causal effect is close to 5? Well, that depends on how precise the OLS estimator is in our setting. We can determine the precision by looking at the standard error. If the standard error is small, then the estimator is precise. So if you're facing a small standard error, we should probably believe that the causal effect is pretty close to 5. How close is pretty close? We can't answer this question because we're missing some important tools. We're missing the tools of statistical testing. That's what we're going to talk about in the remainder of this video. To introduce the ideas behind statistical testing, let's consider a simple example in an intuitive setting. Let's suppose that you have a friend who you like to play dice games with. Your friend brings their own die and says, "This is a fair die." In particular, suppose that you are playing a game where the probability of rolling a 1 is somewhat important. So your friend says, "The probability of rolling a 1 with my die is 1/6, since it's a fair die." And you don't really believe them because you know they like to twist the odds a little bit in order to win. But you're willing to play devil's advocate. So you say, "Okay, I believe you for now." And your friend will say, "Let me demonstrate how fair my die is. I will roll it 60 times. And you will say, "Okay, but I'll be here and I'll watch. I will count the number of ones." And if at the end it looks funny, then I will stop believing that your die is fair. That means I will stop believing that the probability that your die rolls a 1 is 1/6. Here we already have all the ingredients of a statistical test. First off, we have a statement that we are trying to disprove. This is called a null hypothesis. When constructing the test, we operate under the assumption that the null hypothesis is true. Why we do that will become apparent shortly. Next, we collect a random sample. Then on the sample, we compute a number. A fancy name for a number computed on a sample is a statistic. So this is what is called the test statistic. Since it is computed on a random sample, it is also random. Finally, we have a decision rule. This decision rule tells us for what values of the test statistic we stop believing the null hypothesis. But instead of saying that we stopped to believe the null hypothesis, we say that we reject it. We haven't really defined what the decision rule looks like exactly. What is it that makes a test statistic look funny? To derive a decision rule, this part here is important. What we do is we take the null hypothesis really seriously and we wonder what does the distribution of the test statistic look like if the null hypothesis is true? What is neat about this example is that the distribution is completely defined from the null hypothesis. It is a binomial distribution. Details don't matter here. What matters is that the distribution looks like this. We can use this plot to look at the probability of rolling 1 a certain number of times. For example, the probability of rolling 5 ones would be this probability. So this is the correct probability if the null hypothesis is true. The expected number of ones rolled if we roll 60 times is 10. So on average, every 6th roll will be a 1. And not surprisingly, this is also the most likely outcome. And a lot of the probability mass is concentrated around 10. Now, what would be a good decision rule? We certainly shouldn't reject if we observe 10 ones. Should we reject if we observe 9 ones? Suppose that our friend is honest and they are indeed using a fair die. If we reject if they roll 9 ones, then we accuse them of cheating with fairly large probability, and we would, in that case, would probably lose the friendship. We don't want to lose an honest friend with high probability. So this is probably not a good decision rule. If we want a small probability of losing an honest friend, we probably shouldn't reject at 11 ones either, and maybe not at 8 or 12 ones. So maybe let's say that we deem all number of ones between 5 and 15 acceptable. That means we will reject if our friend rolls either 4 ones or less, or 16 ones or more. In these cases, we will determine that our friend was cheating. We can illustrate this decision rule like this. So we will reject for these outcomes. And if we add the total probability mass for the outcomes where we reject, it will be less than 6%. That means if we have an honest friend, we will falsely accuse them of cheating with probability less than 6% using this decision rule. There is a price for keeping this probability low, and the price is that we may not detect a cheater. For example, with this decision rule, we're not rejecting if we see 5 ones. Now 5 ones is the likeliest outcome if this probability is 1 over 12, so our friend is massively cheating. In general, there is a trade-off between keeping honest friends and detecting cheaters. A way to formalize this trade-off is to talk about the types of errors in statistical testing. We can make different kinds of error depending on whether the null hypothesis is true or false. For the null hypothesis, we often write H subscript 0 for hypothesis 0. Our null hypothesis is that our friend is being honest. That means that our friend rolls a 1 with probability 1 over 6. Recall that we don't really believe that the null hypothesis is true. We suspect that our friend may be cheating. We only adapt the null hypothesis in order to generate evidence against it. If you want to be flippant about it, we are only going along with this assumption in order to show how ridiculous it is. So what we really believe is that the probability of rolling a 1 is different from 1 over 6. This hypothesis is called the alternative hypothesis. This hypothesis is called the alternative hypothesis. Sometimes we just write H1. By disproving the null hypothesis, we show that the alternative hypothesis is correct. In our setting, By proving that our friend is not being honest, we can show that they are cheating. And this is what we set out to prove in the first place. Note that with the way that we have defined cheating here, there's only one way for our friend to be honest. The probability of rolling a 1 has to be exactly 1/6. But then there are many ways for them to be cheating. So the probability of rolling a 1 could be 1/3, that would be cheating, or it could be 1/12, that would also be cheating. So the alternative actually comprises many probabilities of rolling a 1. Such an alternative that allows multiple parameter values is called a compound hypothesis. Alternative hypotheses are very often compound hypotheses. An hypothesis that allows only one parameter value is called a simple hypothesis. Null hypotheses are sometimes simple, but there's no rule that they have to be. There are also settings where we want to test null hypotheses that are compound. I've written these in blue to indicate that they are determined by the population. In other words, the veracity of these hypotheses is determined by reality. We may be living in a world where the null hypothesis is true and our friend is being honest. Or we may be living in a world where the null hypothesis is false and our friend is cheating. Our test will either reject or not reject. If the test rejects, we adopt the belief that the null hypothesis is false. This means that we adopt the belief that the alternative hypothesis is true. If the test does not reject, then this means that we don't have enough evidence against the null hypothesis. In this case, we are staying agnostic about the validity of the null hypothesis. I've written the test decision here in orange to indicate that it depends on the sample and is therefore random. Now we've ended up with a nice 2x2 matrix with 4 entries. In this column, we end up making a very strong statement about the nature of reality. So we're setting ourselves up for either a huge success or a massive failure. We experience a success if the null hypothesis is false and we reject. In that case, our friend was cheating and we have the statistical evidence to prove it. This is exactly what we were hoping for. If the null is true and we reject it, we make a huge mistake. We end up believing that the null hypothesis is false, even though it is true. We think we have learned a fact about reality, but this fact is incorrect. In our example, we now believe that our friend is cheating, even though they are being honest. Rejecting a true hypothesis is called making a type 1 error. The stakes in this column are a little lower because we end up being agnostic, so we don't make a statement about what we think reality looks like. And since we're not making a definite statement, we can also not be really wrong. Still, you may find it disappointing to end up down here. In this case, our friend was cheating, but we haven't gathered enough evidence to prove that they are cheating. You may call this a missed opportunity to disprove a null hypothesis, or in our case, a missed opportunity to reveal a cheater. This is called making a type 2 error. Now you may wonder, what about if we end up here? Well, if we end up here, everything is still working as intended, but it's not very exciting. so I would give it a gray smiley. Why is everything working as intended? Well, we set out to prove that our friend is cheating, but they weren't cheating, and our evidence didn't say they were cheating. So that's a win in my book. You may still think, if my friend is honest, shouldn't the data tell me that they are being honest, rather than me just being agnostic about them being honest in the end? Well, unfortunately, that's not how statistical testing works. If you want to prove that your friend is being honest, you have to choose the null hypothesis that they are cheating and then disprove that new null hypothesis. In statistical testing, we can only learn through rejection. We now discuss the size and the power of a test. We consider a variation of our previous hypotheses. We'll keep the null hypothesis, that'll be fine, but we'll change the alternative. We'll have the alternative say that the probability of rolling a 1 is 1/12. This means we're assuming a world where there's only one way of cheating, and that is to have a die that rolls a 1 with probability 1/12. There are no other dice in this world. You either have a die with this property or a die with this property. Obviously, our alternative hypothesis is now simple. Having two simple hypotheses keeps things really simple for us right now. We'll consider composite alternatives later on. We know that rejection depends on the sample and is therefore a random event. As such, it makes sense to think about the probability of rejection. To determine this probability, we have to decide in what world we live in. It would be different if our friend is being honest or our friend is cheating. Let's suppose that our friend is being honest, so the null hypothesis is true. To indicate that we are computing this probability under this assumption, we can write like so. So this gives the probability of the test rejecting for populations where the null hypothesis is true. If we reject a true null hypothesis, we are committing a type 1 error. So you can think of this as the probability of type 1 error. This is also called the size of the test. The size, as I've defined it here, is also called the empirical size of the test. Then there's also the nominal size of a test. The nominal size is the intended size of the test. This means if a test has nominal size 10%, then it is constructed in a way that is supposed to guarantee that it has empirical size 10%. But this may not always work out in practice. For example, a lot of tests work really well only in large samples. That means that if you apply them with smaller sample sizes, there can be differences between the nominal level and the empirical size of the test that you experience when you apply the test in real life. Using similar notation, we can think about the probability of not rejecting if the null hypothesis is false, so if we are operating under the alternative. Not rejecting when the null hypothesis is false means committing a type 2 error. So this is the probability of type 2 error. What does it mean if a test has, let's say, low probability of type 2 error? Well, in our setting, it means if we are facing a cheater, we are more likely to end up here than end up here. This means we are more likely to find evidence that they are cheating than we are to find insufficient evidence. A test that is good at rejecting a false null hypothesis is called a powerful test. In our setting here, with a simple alternative, we can simply define the power of a test as 1 minus the probability of type 2 error. This discussion here gives you a very good idea of what people mean when they talk about the size of a test or the power of the test. The exact definitions here would get a little bit more complicated if we were to consider a more general setting with compound hypotheses. Why is that? Well, suppose that we have a compound alternative. This means there are multiple ways for your friend to cheat. Now, this probability is ill-defined. It doesn't really define a unique number because it depends on where we are in the alternative, or in other words, it depends on how our friend is cheating. We will ignore all these complications. The simple setting here already gives us a very good idea of what size and power are.